Let's start now. Hi everyone. Warm welcome to one and all from Sahaj AI. I'll just give a little bit of introduction about Dev Day. Dev Day is an event organized and hosted by Sahaj AI. We host talks covering a broad range of topics, including data science, software systems, data engineering, and whatnot. And within the area of data science, we have hosted talks in the areas of computer vision, natural language processing, speech and audio processing, etc. So today, for this particular edition of Dev Day, we have my friend and very esteemed speaker, Professor Dr. Shekhar Nayak, with us. I was fortunate enough to work with him for a couple of years. We were lab mates during my PhD days and his PhD days. He obtained his master's degree from IIT Delhi and his PhD from IIT Hyderabad. Later, he worked with the Institute of Infocomm Research, which is an A-star R&D center in Singapore, and with Samsung R&D Bangalore. In both these places, he worked rigorously on building speech-to-text conversion systems or automatic speech recognition systems catering to low-resource Indian languages. And currently, he is working as an assistant professor at the University of Groningen and building speech technology for multiple languages. A warm welcome to today's Dev Day, Professor Dr. Shekhar Nayak, and a warm welcome to all of you to this session. You can ask if you have any questions during the talk. You feel free to post your queries in the chat box. He can take it up when there is a break or as he as he figure out suits himself. So yeah, that's all. Welcome everyone.
Thank you, Kartika, for so kind introduction, and good evening to everyone, and welcome to this presentation where we'll talk about the language resources and methods for under-resourced speech systems. I am Dr. Shekhar, working at the University of Groningen as assistant professor in voice technology program, which is a MSc program here, 1 year's master's program. So essentially, like, we work on cognition, speech synthesis, and allied areas. So jumping into the presentation. So today's presentation would have majorly as we have just discussed the title. So the resources, language resources, and also like some of the methods for developing speech systems in under-resourced languages. So the languages which have less amount of transcribed data available, publicly available. So how to build speech systems such as automatic speech recognition, which is like speech to text, and then text to speech, basically in multiple languages, multilingual ASR and multilingual text to speech. And then we'll also touch upon like zero resource speech processing, which is like when we do not have any transcribed data available, we just have the audios, how we can use that to build speech systems, working towards that. And finally, an emerging area which is like coming up in the recent times, unsupervised speech recognition, which does not require like parallel like speech and text to train the recognition systems. So we'll try to touch upon that based on the time. So going into like the first multilingual speech recognition. So basically speech recognition in the traditional sense, the hybrid speech recognition systems basically conversion from speech to text had several different modules which used to be independent of each other, and like they used to be trained. So from the speech you extract features, and then you train an acoustic model to map the features to the corresponding text. So there is an acoustic modeling part in the traditional speech recognition system. Then there is a pronunciation dictionary where like you express the words in terms of phonemes or basic sound units. And then you have like a language model which will assign probability to the word sequences. And then you have a decoder which will search the like most optimal word sequence to produce the text from speech. So this is the traditional speech recognition pipeline. I hope it is audible, it's clear audio and the slide.
Yes, yes.
Okay, so this is just the overview of how like the traditional hybrid speech recognition systems used to be, and they used to have different components which used to be separately trained. And then you had like multilingual speech recognition in a traditional sense, where you build the recognizers for each language separately. So you have n number of languages. Let us consider an example of like Indian languages. If you have Tamil, Telugu, Gujarati, Hindi, Kannada, and so on. So you have different languages. So you build such recognizers, the hybrid models for each language separately. And basically you should have a language identification system which can identify from the speech which language it is. If it is language one, it should go to the monolingual recognizer one, and then it will produce the corresponding text. Otherwise it should go to the whichever language is detected by the language identification system. So that's like a traditional like multilingual speech recognition pipeline which involves language identification. And obviously like such multilingual ASR is like prone to any errors in like language identification, and you can recognize only one language at a time, and basically you have to switch from one recognizer to the other.
Yeah.
So you have to switch across the recognizers. So there is a delay, and also there is like no knowledge sharing across the recognizers. So this is a like traditional multilingual ASR. So you have like each of these components, like the acoustic model, pronunciation dictionary, and language model has to be built for each language. So this example has like English, German, and Chinese, and some other languages. So you have like for each of these languages you have acoustic models. So there can be a multilingual acoustic model which shares the knowledge across these languages. Similarly, there can be a multilingual language model which shares knowledge across these languages. So basically, like the difference between the two is that like you can recognize several languages simultaneously in a like completely multilingual recognizer. So what are the applications of like multilingual speech recognition? So as we see in like mobile devices, so you have different like okay Google, the Google Voice, or you have Samsung's Bixby, or you have Amazon's Alexa, and so on in the eco devices. So basically they should be able to identify, they identify the language, and then like they can recognize the text. So you need like low memory requirement to place the ASR in the mobile devices. So and which should be capable of like recognizing multiple languages. So the other application is to recognize code switching speech. So when a native speaker switches from one language to other, for example, like if you are speaking in your own native language, you sometimes use words of another language, maybe English or French or Urdu or whatever it is. So there is a like code switching from like one language to other. So if you have like monolingual systems, they cannot deal with this code switching. So multilingual ASR can help in like recognizing code switched speech, and then building speech recognition for low resource languages. So when you have very less transcribed data available for low resource, you can share the resources across several languages and create like multilingual speech recognition, which can make use of rich resource languages to improve the recognition in the under-resourced scenario. So we have this going into like how multilingual speech recognition is built. So an example of a famous like multilingual speech recognition model is multilingual DNNs, or shared hidden layer multilingual DNNs, SHL-MDNN, which is a popular architecture introduced in 2013. So basically, you have like hidden layers of deep neural network, which are trained using multiple languages. So these hidden layers are common, and this architecture is like a multilingual deep neural network architecture with shared hidden layers. Therefore, the name shared hidden layer multilingual deep neural networks. And these multilingual deep neural networks have been shown to perform better in terms of like word error rate, which is the metric used to uh, compare the performance of speech recognition systems. So these multilingual deep neural networks have been shown to perform better compared to the monolingual deep neural networks. And these hidden layers are basically transferable to new languages. And this is called as like cross-lingual model transfer or cross-lingual transfer. So this is an important uh, milestone in the like history of like multilingual speech recognition, because you have a certain like this deep neural networks hidden layers. They can learn from like different languages, and they can be transferred to a completely new language which was not used in the training of this deep neural network. So in this like work or in this paper, they used 4 different European languages: Spanish, Italian, English, and French, and they trained using the features of these languages, and the outputs are the triphones or synons for each language. That's uh, the output of each output layer is different for each of these languages, and the hidden layers are common. So they trained on these 4 European languages, and they transferred these layers to a completely new language. That is like they transferred these layers to American English, and they also transferred these layers to the uh, Mandarin Chinese, which are like completely different language family groups. And still they have shown that like when you do such kind of like model transfer, it works despite the American English being closer to these European languages, whereas like Chinese being completely different and like tonal language, is still like when you transfer this layer, which is trained on 4 European languages, to Mandarin Chinese, is still it performs better than a monolingual ASR trained with the same amount of very low resource data, like 9 hours of Mandarin data, 10 hours of Mandarin data. So the monolingual recognition, it outperforms by using multiple languages to pre-train together. So here the hidden layers are shared across the languages, and data is pulled from different languages in order to train a better model. And then you do this cross-lingual model transfer to a completely new language, which is not present in the training data. And it can be fine-tuned with like limited data from a new language. So these 4 European languages had around minimum data was like 60 hours for the least amount of hours for a language, and the maximum was 150 hours. So that was the amount of around 60 to 150 hours of data for each of these languages. Whereas the language to which the model transfer was done, whether it's American English or it is Mandarin Chinese, very limited data was used, like 10 hours or 20 hours of data was used for these languages. So this is like a slightly older model. In 2013, this SHLM DNN was introduced. And then like other shared architectures were introduced later, like shared hidden layer, multilingual LSTMs, and similar architectures. Uh, Recently we have seen the popularity of, like, there is a lot of popularity of like semi-supervised or self-supervised models, such as like wave to vec 2.0. And there was a model introduced recently, which is like wave to vec 2.0 XLSR, which is essentially trained on 53 languages. It's pre-trained. It uses multiple data sets. It uses Babel. It uses multilingual Libre speech, and it is trained on like a total 53 languages from different language families. So it's a like huge pre-trained model which is available, and you can see this library, FairSec library from Facebook Research, and this model can be used to fine tune to any new language with very limited amount of data. So this 53 languages are being used to pre-train this model, where it has like this shared quantization layer, quantizer, which is shared across different languages. So from the speech signal, there is a like a convolutional neural network based encoder, and then there is a shared quantizer, which shares the latent representations across the languages. And then there is a like a transformer based encoder, and then there is a contrastive loss based on which it learns. So this is a like very recent model which is pre-trained on like multiple languages, 53 languages. And basically here also they show that the multilingual pre-training outperforms the monolingual models. And also they show that like cross-lingual transfer to unseen languages also works well. So this is like a cross-lingual model transfer is kind of a like concept which works across the models, whether it is like DNN based models or LSTM based models, or it is transformer based models, wave to vec models, very recent ones. So this cross-lingual transfer can work well across like even to the unseen languages. And then they do like supervised multilingual fine tuning in order to instead of fine tuning for each language separately, which is very difficult for like 53 languages, they do like multilingual fine tuning. So
Shekhar, there are a few questions. Do you want to take them now or?
sure, Kartika. So I think, yeah, we can discuss now.
Yeah. Ravindra, do you want to ask?
Yeah. So, Dr. Shekhar, thank you very much for accepting the talk, and it was so informative. I had few questions. So, when you are looking at multilingual model, one thing that is clearly coming out from your talk is it's really advantageous as compared to monolingual language. But then, when you choose those multiple languages, should they be related in some way? For example,
Yes.
yeah. Okay.
Yeah. So like in this example, like the previous one, they even transferred it to like Mandarin Chinese, uh, like from the European languages. So it's like quite unrelated, but still there was a very slight improvement. So there is a catch again, like the improvement is not very significant. It's like 3 to 5% relative reduction in word error rate. So even though like they use 4 languages, like combined data, which is like 400, 500 hours of data in total, and they transfer to a very low resource like 10 hours of data, but even it doesn't lead to like 1 to 2% like absolute reduction. It's just relative reduction of word error rate, very minute. So that's the case. Here they show like when you in this paper, they show that like when you use similar language to do the fine tuning, it performs much better than like quite far away language.
Thank you. And what is the role of a like a evaluator? Like somebody has to be knowing some language to validate this one, or can they be automatically done through some metrics?
Yeah, it can be automatically done through like the scoring. It automatically does scoring of like word error rates and all without.
Thank you so much.
So otherwise, like it's too difficult. Like
Yeah,
anyone to be knowing like 53 languages, it's a huge.
that's
Earlier, it used to be like relatively like 4 or 10, that kind of like number of languages, but now it's like huge.
I'm also curious to know about your later topics on unsupervised learning and zero resource learning. I mean, I'm very curious. I'll wait for that. Thank you.
Any other questions?
When you said automatic evaluation, the test case is still labeled, right?
Yes, yes.
Yeah, okay. Yeah, no more questions from me.
So hi, one more question. So I think the multilingual model shares a common backbone for all the languages. It like when you say it's transferred to Chinese, does it mean like the same model acquired extra knowledge of Chinese language? Is that right?
Yeah, so like the 4 languages which it used, like each language, assuming like it has 100 hours of data each, so it trained on this 400 hours of the 4 languages data, and it was transferred to Chinese, for which like you basically give the features or the training samples just for very less amount of data, so just 10 hours or 20 hours of data, with which you fine tune this model. So you again retrain this model. So the weights are updated using the features from the 5th language, which is Chinese, and also using the like triphones of Chinese or Mandarin. And then again, like the training phase goes on, like the weights are updated, and then it's tested on Chinese with the Chinese samples. So only the softmax layer of the final layer of like Chinese is retained while testing. All others are removed, and just it's evaluated for the Chinese.
Okay. So it's the head alone is replaced. So now the language can be used for Chinese. So my question is, can I mix, like, can I speak English and Chinese at the same time and still get it decoded?
Yeah, you can have like different
larger head, is it?
Yeah.
But will there be no crosstalk? Is it because at a phenome level, like when you say certain like the phenomes, right? The same phenomes might be like your vowels and etc. They might be shared across most of the languages, so it might be easy to learn them at a lower levels. But as you go higher in level, right, when that phenomes combine together to form a word or sentence, right? So then things there is no crosstalk between 2 languages, right? Like, because I'm trying to understand how that 2 different head is able to produce a proper sentence.
So in this model, like while testing, like there will be like just like a one feature at a time, like which is from like a single model. So like there is no like as such, like there can be inherent code switching, but like it's not as such like multilingual data. So at a time, the feature is from like a single language itself. And
Oh,
like the corresponding synonyms are of that particular language.
okay, okay. Sure, sure. Yeah, that's what I wanted.
Sir, I have one more question.
Sure.
Sir, do we need to extract all features during this DNN system based system also? Hello.
Hello.
Sir. Do we need to extract the features during these all system also, or the features are learned or like
No, no.
MFCC and all
In this
that?
case, like the features are like extracted, pre-extracted. MFCC or filter bank features, they are pre-extracted. Means it's
Mean
extracted
what
during
mean?
that time. It's not
Actually, my
learned
question.
through a CNN or something. It's like straightforward, like MFCC or filter bank features, which are extracted and then they are input to the deep neural network.
Okay, so in that, in case of deep systems, deep neural network based systems, we need to extract first features. Things is we need to extract the features.
Yes, yes.
Okay, sir. Thank you, sir.
So so like this kind of like pre-trained model with like a large number of languages which is pre-trained, you can use to adapt to your new language. So like here we have used it like on Luxembourgish speech, and we are also working on Frisian, which is like a local language here in Friesland, and also on Irish data. So these are like very low resource, like 12 hours or 10 hours of that kind of data. And using these pre-trained models and fine tuning on that kind of training data, it still like it performs better than just using monolingual model or a wave to wave 2.0 model, which is pre-trained on English. So you can find several of such models available on Hugging Face. You can see this FairSec and like Hugging Face, where like these models are available and can be used to adapt to a new language. So just discussing the advantages of multilingual speech recognition, we can identify several languages simultaneously, and we can deal with code switching when there is a switch from one language to other. And it can be easily maintained if there is a like shared acoustic model or shared model. And we need like less CPU and memory resources if there is a overall reduction in like parameters as it is shared in across the models. And the applications could be like public information kiosks, voice dialing systems, and so on, apart from the like regular like mobile devices and voice assistants. So what are the requirements of like large vocabulary speech recognition systems? We need huge number of hours of recorded and transcribed speech in the target language in order to train the speech recognition models. So we need a huge vocabulary of words to train even language models, a pronunciation dictionary of that large size. So basically, lack of such data, it has not allowed the development of speech recognition for certain under-resourced languages. So what are the challenges in designing a like multilingual corpus? So you need, first of all, speakers who can speak in, like, for example, that 53 languages, you need 53 language speakers who are experts or native speakers of that language, uh, who should record a large amount of sentences, and those have to be transcribed by expert linguists into the corresponding text, and they should be aligned with the text. So such data set also should be like uniform across the languages in terms of like there should be similar amount of text and audio data for each language. The audio data quality also be similar, should be similar, like the kind of microphone you are using, what kind of channel is there, and then like the speaking style should be same. Like if you are making the speakers read the sentences, it's a different style. If somebody is speaking extempore, then it's a different speaking style. Conversation is another speaking style. So it should be like similar across languages, and the transcription conventions also should be similar. So earlier, the like most common data sets used in multilingual speech recognition were global phone and like Babel corpus. So I am just discussing the global phone corpus, which is 21 languages. So these are the languages. There are Indian languages such as like Tamil, and then there are like African languages, Swahili, Arabic, Chinese, from European families. So different language families, 21 languages, and 100 speakers have read like 100 sentences each, total 300 hours of a speech with 1500 speakers in total. So this can be used for like, this has been used extensively earlier for multilingual speech recognition and language and speaker identification. So this is available through like ELRA, European Language Resources Association. So you can see that like the costs associated with that, like for like commercial use also, is like quite high. Even for academic purposes, like there is a cost associated. So now we are getting like open speech and language resources, which are like free and openly available. So OpenSLR is one such website. So which has
I mean, I have one doubt, sir. Suppose if in terms of data collection, supposing I want to imagine, supposing I don't have any open source data on say 3 Indian languages, any 2-3 Indian languages. Now, is it sufficient, like you said, about 10 hours of data, like I think you said about 100 speakers speaking 100 sentences. Is the data good enough for starting the activity?
Yeah, so essentially like TIMIT is one very good example. Like TIMIT data set has been used in speech recognition from like quite long, like almost 2 decades or more. And it used to be just like 3 hours of, it is still like 3 hours of training data and like 1 hour of like testing and like development data. So still like with TIMIT, like people achieve these days like a phone error rate of like 14-15% or closer to 10%. So still like speech recognition can be built with as low amount of data such as like 10 hours.
And the syllables that have to be spoken, they have to be in a specific manner. I mean, does it have to be wide, like a very variety or wide variety, a lot of contrast has to be there, and a specific words only has to be spoken.
So it depends on like, so if you are building a like large vocabulary speech recognition, which used to be like the terminology, so it may have like some in the order of like some 10K words to like millions of words, unique words in the corpora. But it can be like for low resource, it can be much lesser also. Like there could be like around like 5 to 10K words also could be a good enough starting point as well.
Thank you. Thank you.
So this open speech and language resources, it contains like several open source, like not only like data sets in different languages, and also it has like several softwares which are open source and are used in like speech recognition and other speech technologies. And there are like several already built like language models or language modeling resources, and different several resources for several languages are available through this open SLR. This is like completely free to like download and So there is like another very important one is like Mozilla's common voice data set. So it has now like huge number of languages, like 93 languages, with like approximately like 20,000 hours recorded, and like 14,000 hours have been validated. So it's like the largest publicly available multilingual voice data set, and it's like crowdsourced. It's collected from like the users on internet who record in their native languages, and new languages are always getting like added progressively. So this like common voice data is also used in the uh, wave to wake XLSR, apart from multilingual Libri speech and Babel, which are like more established like multilingual corpuses. So this common voice data is another very interesting resource which can be used for like low resource languages, along with such open source like models, Hugging Face based like wave to wake models, multilingual pre-trained models. So this is like regarding the multilingual speech recognition. So just to summarize that, like we are recognizing text from like speech in multiple languages. And in traditional speech recognition systems, we used to build like individual components for every language. Here, in multilingual speech recognition, we are sharing the resources from across the languages, and uh, uh, building the models in a shared way, and it reduces the memory footprint of speech recognition for mobile devices, and it can deal with like code switched speech. So before going to like TTS part, like if there are any more questions.
I
Yeah,
have
so
a quick
Gram
question.
one.
Yeah,
Yeah,
sorry.
sorry.
So
Yeah.
all these models that you've talked about, wave to wake, as well as the shared hidden layer neural network, they are all front ends, right? Acoustic models. And while decoding, we still have a language model in play, or any of these framework end to end.
Yeah, so in wave to wake, like we can do language model rescoring. We can do without language model as well. But in case of like shared hidden layer multilingual DNN, there is a like there has to be a language model, whether it is n-gram language model or it's an RNN based language model, RNNLM or
Okay.
so.
So you're saying wave to wake or model can be used to build an end to end ASR.
Right.
Okay. Thank you.
So
Hi, sir.
there,
I'm
yeah.
a student from IIT Hyderabad.
Excuse me, sir.
Yes, hello.
Excuse me,
Hello.
sir. In real-time recognition, is possible to get a real-time recognition model, acoustic model, language model with wave to wake. Uh, in comparison to CNN or the LSTM, is it possible to get that real-time recognition accuracy to a greater extent? Is it possible? And if it is possible for multilingual data like the Indian languages, Hindi, Tamil, Malayalam, Kannada, let it be not a huge vocabulary, but somewhat shorter or medium vocabulary size for medium vocabulary size. Real-time recognition. I mean to say, when I speak to a microphone, it recognizes at the time, because I'm working on robotics fields. So their real-time recognition is the need of the hour. It should be precise and it should be up to the point. So is it possible to get a real-time accuracy, greater accuracy?
Yes, it is possible to get real time with very low. There will be latency, but very low latency with like less than like 500 millisecond, based on like it is possible to build like real time recognition.
Thank you, sir. But, how to arrive at the models, end-to-end models that wave to wake, how to use that wave to wake to create multilingual ASR models.
So the Hugging Face you can refer to. So it has like the pre-trained models, and accordingly, like you can essentially so there are like wave to wake models trained on like that XLSR 53, and then like fine-tuned on English, or like the base model, which is like just pre-trained on English 960 hours. So you can use these models, and you can essentially like fine-tune them to your own task that's available in this like Hugging Face, these models, and it can be used to fine-tune to your own language. And I'm seeing some more.
Thank you, sir. Thank you,
like,
sir. It was nice. Thank you, sir.
So yeah. So in OpenSLR, you can see like many languages, many even Indian languages that Hindi data set like already like Dr. Kartika has answered, like Gram Vani. So it's like more than 1,000 hours of data available. Similarly, like you have Microsoft's Indian language challenge was there. So I can see like even Dr. Tanvina is there, who was like, they won this competition in 2018 interspeech. So it was essentially Gujarati, Tamil and Telugu, 40 hours each low resource data. So it is still like you can, it should be available through Microsoft's website. So and then there are like certain challenges being introduced by IIT Madras every periodically. So Indian English, Hindi, and then like several Indian languages, there are challenges being organized by IIT Madras on Indian languages ASR, and those data sets are like freely available. You can check them out at the like IIT Madras speech website.
Freely available for academic as well as research use. Just to add. Aravind, you can ask your questions now.
Yeah. Hi, sir. Like, I wanted to ask, is there any linguistic motivation behind multilingual models?
So essentially, like there were earlier the models when like at the time of like this multilingual DNNs and so on, like there was an effort towards building like common label set, common phone set, like global phone set, which is common across multiple languages. Which has like shared phones and like the different phones all clubbed together. So up to like 300 or 400 phones which are like pulled from across languages, that kind of like things were there. But now like with recognition at the like just the character level or word level, it's now not that linguistically motivated, as you mentioned, as earlier.
Thank you, sir. Sir, I had another question on the shared hidden layer MDNN. So, like, how does the performance on the previously trained languages change when we pre-train the network on a low resource language?
So it improved the performance on like each like of the languages which was already used in the training data. Monolingual recognizers, it outperformed for each of those languages, as well as like to the new language where the model was transferred. For that also, like with the compared to the monolingual recognizer, it improved the performance.
Sir, actually, my question was more about, so now that we have trained on all the four languages, when we introduce a fifth under-resourced language, so we would the weights of the shared layers would have been altered, right? So the new performance that we would have that we would get on the four languages, does it improve or does it degrade? Because that we have now that we have altered the weights.
Okay. Yeah, still it should improve, because further you have like so the knowledge sharing across the layers will further increase. Like earlier you had like 400 hours of total training data. Now you add further like 40 or 50 hours of low resource data, so it shouldn't degrade for the earlier languages. Still it should improve.
From couple of papers that I've read, even if it does not improve, the deterioration was pretty marginal. It didn't adversely affect. So when we add progressively new languages, it didn't ruin the already learned language. If that's what if that answers your question.
Yes, thank you.
Right. And like negative transfer is possible in certain cases in such transfer learning models. For a particular language, it can slightly degrade the performance. That is also possible in such architectures. Especially, for example, like when you have like four languages trained together, like one of them, if you have like data which is not that clean, you have like noisy data, and like individually also, like if you train the monolingual model, its performance is not comparable to other languages in the group. It can further like degrade the performance for all the other languages which had like clean transcriptions and like clean audio. So it can also negative transfer is also possible in such cases.
Okay. Then in that case, does it make sense to incrementally include the languages rather than a big bang 20 language model kind of thing?
Right. It depends on like the application or the kind of like work we are doing. So in case like we want to just pool whatever available together and like build a like huge pre-trained model like in XLSR 53 example. So in that case, like it may not make sense to incrementally add, but in case like if we want to develop an application for like 4 or 5 like Indian languages, which is specific, so we may like add the languages incrementally and see uh, how it affects the performance.
Thank you.
So now I'll talk slightly about multilingual text-to-speech. So building text-to-speech for like under-resourced languages. So speech synthesis, we see that like the computers or the like voice assistants speak to us back in a like human-like voice, which is like natural or natural, close to natural sounding. So building such like text-to-speech systems for under-resourced languages, it can be like there are 3 different approaches which are mentioned in like literature. So one is like direct approach, where you use the limited data from the new under-resourced or low-resourced language to build a new voice. Or you can do voice adaptation. You can adapt an existing voice from a related language to the new language. For example, like you already have a like existing recognizer in Hindi, you can adapt it to like synthesizer in like a synthesizer in Hindi, you can adapt it to a related language, maybe Gujarati or Marathi. So that adaptation can be done. Or you can train multilingual text to speech similar to multilingual ASR. So again, like you can switch across the, so this can deal with like code switching, and you may have a common voice, a single voice to synthesize across the languages, or you can have multiple voices to synthesize across different languages. So these are like different ways to synthesize multilingual speech. So the goal of the multilingual TTS is to produce high quality speech in multiple languages, possibly with multiple speakers. So also there are like voice cloning systems which are developed for cloning the voice from like one language to the other. For example, like using an English speaker's voice, you can synthesize Dutch speech without training on like examples which are bilingual, which have like both Dutch and parallel, like Dutch and English speech. So such kind of like voice cloning systems have been developed. And so just sorry, my slides have hanged. Hello.
Yeah, we can hear you.
Okay, yeah. So this is recent like Tecotron 2 based like multilingual speech synthesis model. So it's basically Tecotron models basically synthesize speech from like spectrograms, Mel spectrograms. So this has like from the text you have like the text encoder, which produces the encodings in the text format, and then you have like a residual encoder which learns the prosody or like latent representations from the speech, and you use this like residual encoding and the text encoding in a decoder which produces the Mel spectrogram, and it uses basically speaker and language embedding. So this language embedding basically is giving the language information, and this speaker embedding is giving the speaker information in which the waveform, the spectrogram should be synthesized. And then there is a like vocoder at the end, which is like a wavenet vocoder, or it could be a like in Tecotron 2 based models, it's a wavenet web vocoder. In Tecotron models, it's Griffin-Lim algorithm, which synthesizes the speech from the spectrograms. So input text is basically represented as UTF-8. So it doesn't matter like any language you can give, and it can like you can use the UTF-8 encoding in order to get the for the front end of the multilingual synthesizer. And basically it trains using adversarial loss, and basically you get like disentangled representation of the text and the speaker identity. So there is a very nice example available by the authors here, like where they change this speaker embeddings, and so this is like original individual language sentences synthesized in English, Spanish, and Mandarin. So the text is available here, the first commercial flight. So I'll just play.
In 1919,
The first commercial flights took place between the United States and Canada in 1919.
The first commercial flights took place between the United States and Canada in 1919.
And this is a different utterance in Spanish.
Una rival que había tenido una historia amorosa con Christopher.
una rival que había tenido una historia amorosa con Christopher.
Una rival que había tenido una historia amorosa con Christopher.
And this is the third language, Mandarin. So the Mandarin.
第一班商业航班在1919年来往于美国和加拿大。第一班商业航班在1919年来往于美国和加拿大。
第一班商业航班在1919年来往于美国和加拿大。
So these are like independently, like each language is synthesized. These are test utterances which are not in the training of the models. Now you can see example of like cross-language voice cloning. So the basically English speakers now English speakers voice will be used to synthesize Spanish and Mandarin. So this is the reference.
The theme of the movie is reincarnation.
So this English speakers voice will be used, just cloned into Spanish and Mandarin. So there is no parallel training done. This is just cloning from English to like Spanish.
Una rival que había tenido una historia amorosa con Christopher.
And
no somos seres aislados, formamos parte de la cadena universal de la vida.
A similar example like for Mandarin. So this is the
continue to follow Pennsylvania 14 South.
And this is like from the English speaker, you are cloning to the.
第一班商业航班在1919年来往于美国和加拿大，它的动机更加务实和政治化。
So essentially, we can see that like these like language embedding is changed, and you are able to like synthesize in a different language. You are able to clone it in a different language than the one with which it was trained. And then there is further like accent control and so on. There are like further examples. When you change these adversarial weights, you can see that like accent level goes from like light to strong. So this is like a Tecotron 2 based like multilingual speech synthesis example. So again, talking about like resources in like multilingual text to speech. So there is a like a simple for all project, which was by University of Edinburgh and some other universities, which was created to produce freely available tools for building text to speech synthesis systems without with very less supervision using existing available data. So this Tundra corpus was created. It's a multilingual corpus created from audiobooks. So there is no recording done as such, like in a studio environment, several speakers sit and then record and then transcription is done. That traditional way, this corpus was not built. It was built by just using the audiobooks. So you have audiobooks available on internet. You may also have the text format of the book available. So basically, this data is called as like found data. So it's just found on internet. It's not created. So they use like their toolkit and they pre-process the audios. They segment the audios at the sentence level because the audiobook may be very large, 2 or 3 hours of audio together. So they cut it at like sentence level, segment it, and then like align them at the like book level or chapter level. So they create such kind of like multilingual data just from the audiobooks with minimal like supervision. So they do speech pre-processing, noise reduction, normalization, de-reverberation, removing any echo, and then they segment it, and then basically they do forced alignment in order to align the speech and the text. So from the audiobooks, speech files and the audiobook like text files, the text format of the book, you can create the like text to speech training data by like these steps, like cleaning the data, speech segmentation, and then like aligning the speech and text, and then basically you can create the models, TTS models, you can train them. So this is just an example, like so these many languages, 14 languages it has, European languages, and these are the like audiobooks which were used to create this data set, and these are the number of hours of data and other statistics. So basically multilingual speech synthesis refers to like synthesizing speech across multiple languages in a common voice or like with multiple voices. And again, like traditional text to speech, we require each component to be specifically designed for a new language, whereas like multilingual speech synthesis, you can have a like a common model to build voices for like under-resourced languages using other language resources. And you can use voice cloning to replicate voice to another language without training on like bilingual or multilingual data. And as we have seen, like it is difficult to get like multilingual data in multiple languages because you require expert speakers and transcribers and designing a corpus carefully. So you can use the found data available on internet, like freely available audiobooks to create multilingual data sets. So the audiobooks which are available, they may not be just from the professional speakers, or so they may not be of very high quality, and the text may not be present or aligned. So these things we have to take care of. And like there are tools available which can do the pre-processing, segmentation, and alignment for creating such multilingual corpus. So any questions at this stage?
I have one question. Go ahead.
Hello.
Go ahead, please.
Sir, suppose we want to develop a speech recognition system using deep learning. Then what frame do you suggest? There are many frames: PyTorch, Tech, and TensorFlow, and all that. Which framework is more suitable for developing speech recognition system using deep learning?
All of these have like good like models available. You can have like you can get like pre-trained models, whether it's like PyTorch, TensorFlow, ESPNet, or like new further tool kits are coming like SpeechBrain and several others. So you can choose the one in which you are comfortable with. There are like Python based or C++ based, or like shell script, like which is the front end of certain like CalD or ESPNet. So you can choose whichever is like suitable to you, and also like based on your application or so you can select.
Thank you, sir. Thank you.
Yeah, I have one doubt. Whether is there any commercial, for example, audio books are freely available. Should we need any permissions to make use of the data, or can that be used commercially for building commercial models?
No, we have to take care of the like copyright, those things.
Okay, we need to take permissions from them.
Yeah. Until unless like they are like free and like under like Creative Commons license, or like which can be used to recreate. So that we have to take care of.
Sir, one more question. As we say that in deep learning, the features are learned, but as you told that we have to extract MFCC and all that. Is there any we necessarily have to extract, or is there any way to learn the features also? As in case deep learning, it is said that in deep learning model itself learns the features. Is it true, or we need to extract again features?
No, so for example, the Wave2Vec, the 2.0 model, you can use just like the normalized audio, raw audio you can use without extracting any features. You can use like, you can design architectures. You have like several architectures available where like there is no explicit like extraction of feature required. You can train them from like a raw audio, raw waveform.
In case of these deep learning framework, also in case of PyTorch and all that, I can take raw speech data also without extracting the features.
Yeah, in certain models, yeah, you can do that.
Okay, thank you, sir.
Yeah, so if there are not no more questions here, like I'll just touch upon like zero resource speech processing. Basically, like the motivation behind this is also like from like my PhD work done with like Dr. K. Sri Ramurthy at IIT Hyderabad. So basically, the zero resource speech processing essentially requires no transcribed audio as such for building the speech systems. So for training a speech recognition system, you may need the audios, and you need the like transcriptions, you need these like manually marked boundaries. You have these transcriptions, like this is utterance from like English, timid data set. Water all year, wash water all year. So this is a segment from that sentence. This is water all year. So basically you need this kind of like transcriptions, manually marked phoneme boundaries or word boundaries. So these transcriptions and the audios both are used to train a acoustic model. So from a speech, you extract the features such as MFCC or filter bank, and then you use this corresponding manually marked labels such as phones to train classifier or acoustic model in order to build the speech recognition systems. So the Google's speech translation, like which was like introduced in 2019, requires like around 49,000 hours of transcribed speech with like 100 million training examples. Similarly, Google's voice search, it has around 2 million search utterances or 2,000 hours of data on which it is trained. Similarly, Microsoft's English conversational ASR is trained on 2,000 hours of transcribed data. So as we have seen, like this Mozilla's Common Voice project, it has like a large amount of hours of like open source transcribed data in multiple languages, but it is crowdsourced and it has certain times it has noisy transcriptions. Then we have like Amazon's Alexa. So certain times like these devices record our voices from the devices, and they are used to transcribe. The employees transcribe that kind of data and reuse this data for building models. So there are like even privacy issues in such like data collection. So the motivation behind zero resource speech processing is that like speech transcription requires both human experts as well as like recorded speech content should be available. So even for the example of like audiobooks, we need those audiobooks and like the corresponding text, like the recorded content should be available. So even 1 minute of speech transcription may require like up to like 30 minutes or even up to 2 hours, depending on the transcriber's skill. And endangered languages, certain endangered languages lack both human experts as well as like speech content availability. So for such languages, if you want to build speech technology, because it is also important to preserve such languages. If you build a speech technology for such languages, such as a speech synthesis, that language will be preserved even though it has very less native speakers living. So like Menominee is a example of like endangered language, which is Native American tribal language, which has less than 10 speakers living. So total languages of the world are like close to 7,100, and out of which 300 are already extinct, and 1,600 plus languages have less than 1,000 speakers. So the reasons for extinction may be unavailability of speakers, and like so if you do not have enough online content or data mining tools, it will be still difficult to build speech systems. So the solution to this problem is like creating virtual transcriptions. So virtual transcription is like in terms of like, instead of having these manually marked, this somebody listens to this speech signal and marks that this region is like phoneme water. So then t and so these are like manually marked. Somebody listens and marks these like phonemes or at the word level, that this is water, this is all, this is ear. So instead of that, like, can we transcribe it like automatically through a computer? Can the computer mark this is a different label, this is a different label, this label and this label is similar, this phoneme and this phoneme is same, so there should be a similar label assigned to these units. So that means you have to split the speech, you have to segment the speech into non overlapping, you need these regions, different regions. You have to segment the speech into like varying length segments, and then you have to cluster these in order to like get unique phonemes or unique spoken units in order to build virtual transcriptions. So these virtual transcriptions can be obtained automatically without any manual effort. And it will be in terms of like non-linguistic units, virtual labels. These virtual labels need not be particularly word, syllable, or phoneme. It could be a mixture of those. It could be like completely different. So it will be automatically determined by the computer. So the zero resource speech processing, the task is to discover in an unsupervised way linguistic units from the speech. So if I can identify automatically word level or sub-word level units from the speech, then in an unsupervised way. So that's the aim of the zero resource speech processing. And the goals are like to generalize across languages and across speakers. And the applications are like keyword spotting, audio document classification, or language identification, and so on. So this is inspired from language acquisition in infants, where like infants in their first year of growth, they learn certain phones and then certain words and then some aspects of grammar without any supervision or feedback. So they are not taught by like they do not go to formal school or so. So within first year of their growth, they listen, just listen, and from whatever the audio they get, without any feedback, they learn certain aspects of the language, the phonetic level, word level, grammar level. So similarly, and they can discriminate between speech sounds as per the phonetic category without any prior language experience. So if that is the case, can the computers be taught to learn just by listening to the language without any supervision, without any transcriptions, without any human intervention? Can they be taught to learn certain aspects of the language? So for that, like acoustic segment models are built in order to do the zero resource speech processing. So basically the speech is first segmented into this like varying length units. So the computer should be able to, the algorithm should be able to mark the boundaries where there is a change in the speech characteristics. So we should be able to identify that this region is different from this region. So the algorithm should be, so that is done by like segmentation. So speech segmentation in an unsupervised way, and then segment labeling. So basically you cluster these segments. Now you have got these different length segments. Now you cluster these segments and get certain labels. So you have like, you can have like 50 labels or 100 labels, whatever. And that number of clusters or number of labels that will be used to transcribe any utterance. So this is the cluster indices will be used to label this utterance. So we can see that this phoneme and this phoneme is same. So it should be marked by same virtual label 2. Whereas like the different segments are marked by different virtual labels 1, 2, and so on. So and then you can do the acoustic modeling in a similar way you used to do with the manually marked phones or labels. So now you can use these virtual phones and the features derived from speech to train the acoustic models. So this is acoustic segment modeling, and then you can train like a speech recognizer. You can decode using these acoustic segment modeling units or virtual phones for any given test utterance. So you can create a speech recognizer out of it. So I'll not go into much details because we have very less time. So I'll probably provide some reference. So this is an example of like automatic segmentation. So you can see that there are like, this is the original boundary and this is the boundary marked by this kernel gram segmentation, which we had done in 2017. So this almost gives like boundaries closer to the actual boundaries. There are some missed boundaries and there are like some spurious boundaries as well. So then you do the clustering and then you basically do the entire acoustic modeling, and you get like basically virtual phones which can be used to train the speech systems in an unsupervised way. So this is an example of like virtual transcription after like segmentation, clustering, labeling, and like training an acoustic segment model. So this is the same like utterance, water, all, ear. So our virtual transcriber marks these two with the virtual label 32, which is obviously not correct because this was va and this was a. So it should have been different virtual phone, but then it marks like a different unit to this entire portion, and then it marks a similar phone 32 here. So this is consistent. You can see from the manually marked boundaries. So you get these virtual labels which can be used to train speech systems. So there are like these applications of zero resource speech processing, spoken term discovery, identifying like word or subword units from a speech, speaking rate estimation. Can we find like how many syllables or phonemes are spoken per second for different speakers? So that can be done in unsupervised way. We do not require any transcriptions for that. So it can be done in a zero resource manner. Then spoken language modeling can be done. So without using any text, you can do language modeling. Spoken language modeling, which is again an application of zero resource. And then speech synthesis without text. So just from the speech, can you derive some embeddings, and using those embeddings, can you synthesize speech in another speaker's voice? So that's also like application. So there has been a zero resource challenge, zero resource zero resource challenges, which have some of these tasks like TTS without text and spoken language modeling. And then you have other applications such as unsupervised language identification or unsupervised speech recognition. So I think time is very less. If you have any questions, we can discuss that. This is like recent works on unsupervised speech recognition, which you can refer to later. Like Wave to Vec unsupervised is a model by like Facebook Research, and this is another like unsupervised speech recognition model. So they do not require parallel text and audio data. You can have mismatched text and audio data, and still you can do so. They are not exactly like unsupervised, just using audios, but they use text which is different than the basically unmatched text they use for building the speech recognition system. So if you have any questions, we can stop here and discuss. Hello.
Sir, one question. These virtual transcription should have the same level as the language names, age or work or this type of things, or it may may have any virtual name for transcription also.
Can you repeat once?
So suppose we have generated by this unsupervised learning some clusters, then these clusters should have the same name as our phonemes in existing language, or we can have different names for that also.
So they will be like different from like the actual phonemes or like words in the language. So they will be based on the like number of clusters which we are selecting in our clustering process.
But suppose the cluster matches to O, but then we should say that this correct or something else. We can also write. We can say other cluster. I think. I mean, should we write the same phoneme to that cluster, mean to that cluster, or we can also have some
No,
other
there
cluster
is no
also?
one-to-one mapping between like the phonemes and the like that clusters actually.
Okay.
There would be certain phonemes in the language which will not be covered by our clusters.
Yes.
And there would be certain clusters which may be overlapping with multiple phonemes.
Yes.
So it's not one-to-one mapping. And like if you select like 50 clusters, we have seen like it will be closer to like the phonemes in the language. If you have like larger number of clusters, like 200, 300 or 500, it will be closer to like the syllables in the language, the subword units. So essentially it depends on the like number of clusters, and it will not have like one-to-one corresponding with the correspondence with the actual linguistic units.
It may be syllable or it may be phoneme or something else.
Yeah, it can be syllable, phoneme, word level, or subword level, or it may not have a one-to-one corresponding. Like it can be from middle of a phoneme to like another phoneme, like a triphone or a biphone, but like it could be like not exactly from the it could be a phoneme and silence combination or something like that. Or even noise labels could be a particular cluster, something like a laugh or cough, or that kind of like it could go also be, if it is not clean data, it could be another cluster from the data. Because it's unsupervised, so there is no like specific, it could be but it is usually like from like similar to like yeah, is there any question?
Yeah, Shekhar, there is a very interesting question in the chat.
Okay.
For no script language, how to do the transcription?
Okay. So in case of like this like zero resource, you do not need like any script. So because just from the audio you are segmenting it based on like wherever there will be a change in speech characteristics, your segmentation algorithm should like give a boundary. So and then you have to cluster it. So but it will be like virtual transcription, so it has its own limitation. You cannot do like a speech recognition out of it, but like you can do certain things which, sorry, the voice is breaking.
It's okay. I think we can hear you.
Yeah, so certain things like a speaking rate estimation or certain applications may not require with the virtual transcriptions we can deal with it. So,
GPUs.
Okay. Are there any more questions?
is there any software for virtual transcription? So like you can the zero resource speech challenge like 2020 or 2021, it has like already available like open source model, like the baseline model. It's a like a CPC model, and it's available freely. But I'm not sure like any software like for commercial use or that kind of, I'm not sure, but like that zero resource speech challenge has like certain like baseline models, and other like the participants also might have certain models which would be like publicly available through GitHub also. So you can have a look at the just I'll go through the references. These are like on multilingual speech recognition. This is the SHL MDNN one. And then you have multilingual text to speech. These are like zero resource. So the zero resource speech challenge 2017, and then 19, and then 21. So these you can refer. So you will get like for the latest challenge, you will have the CPC based models available open source. And the zero resource, that virtual transcriptions I was discussing. So this unsupervised speech signal to symbol transformation for language identification. This reference, or even like the ones on like zero resources speaking rate estimation, these like are based on the work which I discussed. And these are like open SLR resources, common voice project, and then Hugging Face, that open source pre-trained models. And these are like different ASR and TTS toolkits, Caldi, Merlin, PyTorch based ASR and TTS, and some tools. Yeah. So does real-time ASR can train and function without GPUs, can be trained without GPUs? So most of the deep learning based models require GPUs, but you can get certain models for which you can get like the GPUs freely available from like Google Colab, or so the models which are available through that you can get GPUs available directly freely, but those will be limited for like a few hours. You can get those GPUs, but if you want to train for a longer time or on huge data, then like you will require dedicated GPUs.
Okay, if there are, oh, yeah. Any more questions, comments? Yes, Tanvina, you're absolutely right, because in speech, it's also the humongous amount of training data that we have to deal with. Yeah.
Yeah, and mostly because I see the questions are mostly like people who want to use their systems. So when it comes to using, I think you don't need a GPU. You can do a CPU based inferencing also. So I think maybe the question was, is GPU needed? But yeah, training it's good to have, but decoding or inferencing, you can go without it also.
Yes, yes, perfect. Okay, if there are no more questions or comments, let's just conclude. So I would like to express our heartfelt gratitude from all of us at Sahaj, and all of us in the audience who have tuned in today for the Dev Day, to Professor Dr. Shekhar Nayak. The talk was really insightful. I'm quite sure we all benefited from the talk, and we have obtained valuable takeaways. Data scarcity is a real challenge that all of us as data scientists had addressed at some point of our data ML life cycle. And today, Dr. Shekhar has given insights into the open to use resources, and a nice, concise introduction and description about the strategies in this speech and audio domain, data scarcity in speech and audio domain. Thank you so much. Ravindra, do you want to add a few words? Shekhar Ravindra is our global head global head data science at Sahaj. Is he here?
Thank you very much, Dr. Shekhar, and thanks to Dr. Kartika. It was so insightful. I mean, really, after hearing that, I mean, I kept thinking, why didn't you even explore that area so far? Thank you. It was so insightful, so motivating.
Thank you so much.
Yeah, thank you for putting the effort, sparing your time, and delivering this talk. We are really glad that we invited you. We all benefited quite a lot.
Thank you, Kartika. Thank you so much for this opportunity. Thanks to everyone for giving your time and listening to this. Thank you very much.
Thank you. Thank you so much.
Okay, folks, we will